So the first talk is will be given by Chenfeng Cao, who's from the Hong Kong University. And the floor is yours now. You can start.
Okay, thanks. I will turn off my camera to obtain a more stable internet connection. Hi, can you hear me?
Yes.
Okay, if you have any questions during this talk, feel free to interrupt at any time. And dear all, thanks for coming. I'm really glad to give the talk at this interdisciplinary summer school of machine learning and physics and chemistry. And I will introduce my recent work about applying machine learning, applying reinforcement learning to optimize quantum algorithms. The title is Quantum Imaginary Time Evolution Steered by Reinforcement Learning. In the previous talks, we already have a clear picture of quantum computing and machine learning. Some quantum algorithms that can achieve exponential speedup compared to their classical counterparts. But currently, we are still in the NISQ era, that's noisy intermediate scale quantum, which means we do not have enough qubits, and the quantum operations are always noisy. A central challenge in this era is to design algorithms that can be implemented on NISQ devices. Many real-world problems can be encoded to a Hamiltonian, with the solution being the ground state. On NISQ devices, we have some well-developed algorithms for ground state preparation, such as variational quantum eigensolver, VQE, quantum approximate optimization algorithm, QAOA, and quantum imaginary time evolution. We will call it QITE for short. These algorithms are also called hybrid quantum classical algorithms because we run the quantum evolution on a quantum computer and also use a classical computer to do some calculation. In this part, we will focus on QITE. First, I will briefly introduce the numerical method called imaginary time evolution. Let's consider a Hamiltonian H, and H can be written as the summation of some k local terms, Hj. If the initial state of psi 0 has a non-zero overlap with the ground state of H, then after long time imaginary time evolution, e to the minus beta h in equation 2. After this long time imaginary time evolution, the final state has a high fidelity with the ground state of H. This process can be classically simulated by Chaucer decomposition. E to the minus beta h equals e to the minus delta tau h1, e to the minus delta tau h2, 3, 4, etc. for n rounds. But this decomposition will induce an error, Chaucer error. The Chaucer error is of order delta tau squared. Delta tau equals beta over n. Okay, imaginary time evolution is a powerful numerical technique, but it cannot be directly achieved on quantum devices because in our world, the quantum evolutions are real time, not imaginary time. But some researchers developed the QIT algorithm based on the idea of imaginary time evolution. And the main idea of QIT is to replace each non-unitary step e to the minus delta tau hj by a unitary evolution e to the minus I delta tau aj, such that the state after the non-unitary evolution and the state after this unitary evolution, they are very close. Here, aj acts on d neighboring qubits and can be determined through measurements. on psi. Psi is the state before this step. The required quantum resource grows exponentially with d. And obviously, when d is large enough, for example, d equals the system size, we can always perfectly find the Hamiltonian AJ that exactly satisfy equation 4. However, this is not realistic since on current quantum computer, we can only implement local gates. So we have to choose a relatively small d. So equation 4 is just approximately satisfied. We still have error. And QIT was proposed in the paper shown here. It was published last year. And I will briefly introduce the local approximation process. How do we determine the optimal Hamiltonian AJ to do the transformation? The parameters of AJ are actually obtained via measurements. We denote the state before the non-unitary step as psi, and the state after this step as psi prime. Okay, so we want to find the Hamiltonian AJ to transform psi to psi prime. And AJ can be decomposed in the Pauli basis, as shown in equation 7. In the Pauli basis, then we measure some Pauli observables on psi and obtain a matrix S shown in equation 5 and a vector B shown in equation 6. We have S and B via measurements. Then we solve the equation S plus S transpose A equals minus B on a classical computer. This one is done classically. Then we can obtain the optimal AJ, the optimal Hamiltonian, do the transformation. And the proof of this optimality can be found in the paper I mentioned in the last slide. If you have interest, you can check the details. Okay, we know the general process of QIT. This algorithm is gorgeous, but it has two big challenges we just mentioned. There exists Chotter error induced by Chotterization, and there exists local approximation error when we use a unitary evolution step to approximate some non-unitary evolution step. We collectively refer to them as algorithmic error. Algorithmic error accumulates with the increase of beta, with the increase of steps. So suppose we want to prepare the ground state of a very large system. We need many steps to find the ground state. But then the algorithmic error will ruin the whole algorithm. The state we obtain eventually is far from the ground state. And here, we use reinforcement learning to tackle this problem. In QIT, there are many steps we just mentioned. We apply some local terms one by one for n rounds. The trivial sequence is term A, term 1, term 2, term 3, etc. We do not alter the main idea of QIT, but we train a reinforcement learning agent to optimize this sequence. The agent is realized by the neural network shown in the right part. It observes the sequence in QIT, input this information, and output the actions. The actions will modify the ordering. Then we run QIT on a quantum computer with the updated ordering, measure the energy of the final state, then input this information to the agent again, and the agent will update the ordering again for many iterations. This is the training process. The agent will obtain the reward and lower the final energy, higher the reward, because we want to prepare the ground state, which has the lowest energy. After training this model for many epochs, the agent will know how to modify this ordering and finally find the optimal one. The optimal ordering produces the lowest energy. In other words, the reinforcement learning agent mitigate the algorithmic error by adjusting the ordering. It just controls these single variables. In this work, we use a model-free reinforcement learning algorithm called distributed proximal policy optimization. It has the actor-critic architecture. The agent has several distributed evaluators. Each evaluator consists of two components: a critic network. The critic network and the actor network, we have 12 evaluators, so 24 neural networks. The critic network computes a policy and will output the action. The actor network computes the policy and output the action. The critic network will assess whether or not it's a good action. And the objective of the agent is to maximize the reward. The agent just cares about the reward. Here we also set a time delay, ND, which means the agent does not obtain its reward immediately. It obtains its reward after some steps. If so, the trained intelligent agent will now be short-sighted. It can take some far-sighted actions. Then the optimization is unlikely to be trapped to a local minimum. Now we show some numerical results. The model we consider here is one-dimensional transverse field aliasing model. We set J equals H equals 1. It's in the critical point. We compare the standard QIT algorithm, the randomized QIT, and our reinforcement learning steered QIT. Randomized QIT means the ordering is randomly shuffled. Okay. We do numerical simulation and also do experiments. Here, field diamonds represent the numerical results, and unfilled diamonds represent the experimental results. They are consistent. And with the increase of beta, the target state, the imaginary time evolution target state, approaches the ground state. Therefore, the obtained energy of all paths decrease in the beginning. However, algorithmic error increases with beta, and this factor becomes dominant after a critical point. The energy of standard and randomized QIT will unfortunately increase after this critical point. And accordingly, the fidelity increase first, then decrease. That's not what we want. And in our method, in the reinforcement learning steered QIT, this model outperforms the previous two significantly for all beta values. As you can see, algorithmic error cancel out in this path because the fidelity between the output state and the ground state grows constantly. The fidelity grows constantly and the energy decreases constantly. There is no error accumulation here. Yeah, the reinforcement learning agent can find the optimal path, a very subtle path. Now we look at the algorithmic error in detail. We define the instantaneous algorithmic error as the squared Euclidean distance. And for beta equals 0.9, here we set beta equals 0.9. The instantaneous error is shown in this figure. The X label is the evolution steps, and the Y label, epsilon, is the algorithmic error. In standard QIT, denoted by the blue line, the error accumulates and eventually climbs to a very high level. Although it fluctuates, but there is an obvious trend of accumulation. It will increase gradually. And in the randomized QIT, denoted by the green line, it performs slightly better than the standard one. and then eventually it drops to the media position. And the path optimized by our reinforcement learning agent is the best. The trend of error shows no accumulation and drops to a very small value eventually. This indicates that the algorithmic errors appeared in the early period, and those appeared in the late period cancel out. We can eliminate errors with errors here. By the way, we did experiments on an NMR quantum computer. This is the molecule structure and the nuclear parameters of the processor. The molecule has 4 carbon atoms. And anyway, experimental results and numerical results match quite well. Here we show the learning curve, okay, during the training. The reward is now stable during the training process, but it converges after about 6,000 iterations. The agent finally learned the strategy and found the optimal ordering. Okay, some conclusions and outlook. In this work, we use reinforcement learning to steer QIT, and the agent is capable of finding the subtle evolution path to avoid error accumulation. The numerical results demonstrate a significant improvement. We also did experiments for some other models, such as MaxCut. Although the results is now shown here, the method, the reinforcement learning steered QIT method, always works. Open question is, can we mitigate the algorithmic errors in some other problems, such as quantum simulation, in a similar way? I think there are many things to be done in the application of reinforcement learning in quantum computing. And here are my collaborators. They all made valuable contributions to this work. And here are some references of QIT. The first one proposed the QIT algorithm. The second one is a variational version of QIT, but they're actually equivalent. QIT has also been applied to estimate many different quantities. The last one is our paper. It's accessible on arXiv. Okay, thanks for listening. I think we can move to the Q&A part.